Okay, thank you. Thank you for the kind invitation and introduction. And so my topic today is deep graph learning, data methods, and applications. So actually, it is more about the current research trends and future research directions about graph learning. And from the three perspectives, that is data methods and applications. So I will go straightly into the concept of what is graph learning. I suppose all of us gathering here to focus on the machine learning on graphs. So graph learning generally refers to that concept, that is machine learning on graphs. So we actually can divide the graph learning techniques into 4 categories, that is graph signal processing based methods and matrix vectorization based methods and random walk based methods and deep learning based methods. So many technique details are neglected today because I would like to introduce more about the problems, about the future directions. So why we focus on graph learning, that is in real world, many data are in graph structured. For example, social networks, transportation networks, protein interaction networks, knowledge graphs, brain networks, and so on. And another reason is that real world problems can be addressed as a small set of computational tasks on graphs, such as drug target interaction identification, knowledge graph completion, recommendations, polypharmacy side effect prediction, so on. And another important reason is that traditional machine learning techniques cannot be directly applied for the graph structure data. That is also why we are now today gathering here to contribute to this workshop. So about the 3 perspectives, that is data, methods, applications. So how we understand about the word deep, I think, how to understand the word deep in deep graph learning. So for data, deep graph learning aims to enhance the data quality and mine implicit relations on or with graphs. And for methods part, deep graph learning aims to promote current graph learning methods in performance, robustness, explainability, and so on. And for real-world applications, the deep graph learning is to benefit real-world complex applications such as group anomaly detection and other downstream tasks as well. So let's first come to the data part. So in the data part, I would like to introduce 2 perspectives of it. One is the augmentation methods that we investigate some of the current graph learning work that is called graph augmentation learning. And the second is implicit relation mining. So first, a graph augmentation learning mainly focused on the problems that caused by the low quality or the imperfect data, especially graph data. So we come across many missing node attributes or some redundant edges or some lack of label problems in graphs. So such problem will be easily handled in non-graph structured data, but will cause a lot of more effects in graph structured data. Therefore, graph augmentation techniques have increasing trends to develop that can be used to handle low quality data while maintaining efficiency and robustness for graph learning. So for the different stage of graph learning, maybe the data processing, pre-processing, and the propagation and representation and optimization, we have different graph augmentation methods, techniques such as node or edges modification, drop node, drop edge, or some attribute completion for missing data, missing node attributes, and some normalization and some contrastive learning and adversarial learning by adding some proper laws in the training and learning process. So for the relation part, I would like to emphasize that one because within graphs, we have a lot of implicit relations. So first, let's come to what is implicit relations. So this is a relative concept because explicit relations can be directly accessed or gained through graph structured data, such as in a social network, and the friendship or the colleagues or the family relations can be easily gained through a social network. But some implicit relations are hidden in that. For graph structured data, such as collaboration network, and implicit relations may refer to a collaborative team that maybe two members, they have collaborated with each other, but they are actually in one team with tight collaborative relationships with each other. And also advisor and advisee relations as well. And for the non-graph structured data, such as images, text, implicit relations can be reviewed with graphs. For example, here I list a methods framework that is for the few short semantic segmentation. The second layer is to build a graph to connect the different features of a single image, maybe the different channels, the different brightness, and build a graph to connect different features together to review the implicit relations among it. So mining the implicit relations on graphs or with graphs are really important in graph learning. And take the big scholarly graph data as an example, because we really dig into this direction for several years, and because we have a really large amount of scholarly big data, and they are quite easy to access and to deal with, and it contains a lot of attributes such as the name, applications, and position, interest, and published papers for the researchers, and also for the organizations, we also have many attributes for it. Such big and complex network provide us to implement our methods to mine the implicit relations. So the next introduction will focus on the academic social network. And we firstly mine an important relationship with an implicit relationship within the academic social network, that is to recognize academic team. So we can see that in the left part of my slides, there exists 4 collaborators, A, B, C, and D. Each of them have different publications, different number of publications, and their collaboration times are listed beside their links. So there is one shortage of the current evaluation metric for the collaboration times, because we can see that A and B and D, they all have 20 collaboration times. But for Scholar D, he has 1,000 publications, and only 20 of them published with A. And for Scholar B, she has a population of 20, and these 20 papers or the 20 collaboration times are with Scholar D. So just simply employing collaboration times to evaluate whether two scholars' collaborative intensity is not fair. So for Scholar B, all her collaboration times are with Scholar D. So we propose a new collaboration intensity index, calculated as the shown equation, to balance this unfairness. And by this collaboration intensity index, we can recognize academic team from academic collaborative network. And the right side of my slides list a real world research team that recognized by this method. And from that, we can analyze that there exist many core teams. There exist many core teams that with really higher collaboration intensity, and within this large research team. And between these core teams, they have some bridge scholars and some extension scholars, so that we come up with a structure that to formulate or to describe an academic team that is core team plus extension team. That is also verified by the research in PNAS. And by that, we, based on the proposed CII index, and together with some other metrics such as academic age and academic vitality, and by some graph learning techniques such as clicks finding mechanism and network influential entropy and some other methods, we can recognize academic team from large-scale academic social networks. And this method allows the teams have overlap members among each other. And the right side, the right side picture with the black background, that is a quarter of real-world academic collaborative network. So they are really in the structure that we have come up with, and it is a truly real-world pattern. So based on this, we come up with another work that is how to formulate an academic team. Here we propose a Liebig spiral to formulate the academic team, because they have really corresponding relationships, such as the members' abilities can correspond to the length of the plank in the barrel. So in our recognition that we all know that cast effect, that is the capacity of a barrel, depends on the shortest length of the plank. But if we tilt and lean the barrel, we can see that that time the capacity of this barrel will depend on the longest one. So we come up with a proposal that we aim to mine some interesting conclusion from the academic social network. That is, we found that the cast effect exists in academic social network, really, and also the anti-cast effect also exists in the academic team. And then based on that, we come up another work that is to recommend proper academic team member for them, because based on real world fact is that people are more likely to collaborate with individuals that they are familiar with. So we first come up with the metrics that to evaluate how the familiarity that the scholars are, and then based on this metric and the shortest distance metrics, we can recommend proper scholar for an academic team when the outlier member is leaving or due to some turnover rate problem. So the next, we may come to the methods part. I suppose here I would like to introduce the methods part into two directions. One is the higher order structure-based graph learning techniques, and another is physics-informed methods. So first, come with the higher order structure-based deep learning methods. There exists a lot of higher order structures in graphs, as we all know that there are some very famous ones such as network motif, K-core and K-trust, hyper-H in hypergraphs. So for K-core and K-trust, they are very commonly used and very traditional methods for the complex network science, because they are very important way to evaluate whether a node is important or not. If we move this node away, whether there will be other nodes collapsed, whether the structures will be collapsed to verify the importance of a certain node in the network. And hyper-H in hypergraphs has a very comprehensive and very strong theoretical basis, and it also is a very promising research directions in graph learning. But today I would like to introduce more of the easy to understand and very intuitive concept and the learning method that is network motive-based. So the network motive, the concept of it comes from the concept of motive in biology. So it is originally refers to a sequence of DNA or RNA, and laterly Milo and other scientists find that in real world networks, there exist many network motive structures with not larger than 8 orders, but appear with really high frequency comparing to random networks. So they call that kind of network blocks as network motives, and they believe that these motives can correspond to real world patterns and can be used to formulate really maybe human behavior or some phenomenon. So based on the network motive, we find that it can truly indeed to formulate some real world patterns. For example, for the social network, maybe Cindy collaborated with Alice, Cindy collaborated with Bob, Cindy collaborated with David, is a way to present the relationship with social networks. And it is also limited by the binary relationship in graph learning. But how can we express with graphs that they all collaborated with each other except Alice and David? So this here is the problem of previous graph learning, that we mainly focus on the direct connection of a certain node. For example, if we conduct graph learning in a traditional way, for the left side, we can see the purple node. The purple node, we traditionally focus on maybe 1 order neighborhood or 2 order neighborhood. Maybe we can aggregate the blue node's information into the purple node, and when we consider about the 2 order neighborhood, we can also aggregate the blue node, the green node's information into the purple node. But how can we formulate the relationships, or how can we describe the relationships among the neighbors? So let's come to the right side. That is, we can see that by using the triangle motif, we can describe the relationships among the neighbors as well as the target node. So by this discovery, we use network motifs to enhance the graph learning methods. That is, we add another important feature, that is structural feature. That is, despite the that is, except for the node attribute features, we also add a node structural features, which is describing by the network motifs, the number, the distribution of it, and finally we aggregate them together and to get the final representation methods. So we will leave out the results, but it really shows some outperformance, except for those networks without many large number of motifs. But it works really good in social networks, because most social networks contain a lot of network motifs, that's wherein these network motifs are corresponding to real world patterns. So based on this, inspired of that work, we also find that motive-based methods can also enhance the performance of link prediction in both the link prediction and the missing link prediction. Because in real world, the networks are always dynamic. We can add many links, but we also have many disappearing links. So with the network motives, we can easily evaluate the strength of a certain link. If it is involved by many motives, it is possibly exist in the future. But if it is not included in any motives, it will have a higher possibility to disappear in the futures. So we come up with a motive-biased random walk methods to guide the model to predict the link or the missing link. So Inspired of the all above mentioned methods, we finally come up with a multi-dimensional framework for network representation learning. And for all input graph data, we firstly refine the graph structures by motif. With the node motif degree and edge motif degree, all kind of current graph representation learning methods can be refined and enhanced. And I will leave out the experimental result. And if you are interested in it, the codes are also provided. And one of the shortage of motif, because it is a kind of induced subgraph, so the finding and computing is very time consuming. So we also provided a solution for large scale network motif computing, that is to give both the theoretical proof and the environmental practical verification to present a parallel computing method and to conduct motif clustering after the graph partition, and the loss is acceptable. So next, I will come into the physics-informed graph learning, I think. So here, I would like to introduce two of the work because I am also a very beginner of it, but I suppose this will be a very promising research direction. So the first work is graph force learning. So here we propose a force model that we use attractive force to keep the two nodes that are in really long distance closer to each other. And we also employ a repulsive force to distinguish two very similar nodes, the representation of very similar nodes, so to avoid the WL test problem. So another work is a quantum graph learning. That is a survey paper we just finished last month, and we believe that quantum theory will provide graph learning a really promising future, because the comparing to the Euclidean data, the non-Euclidean data such as graph structure data has very high requirements in hardware space and speed. Therefore, it can be a computational bottleneck for graph learning. But in quantum theory, qubits carry much more information than bits. So the quantum search algorithms retrieve data maybe with much lower time complexity. And also quantum GNN has shown outperformance in acceleration in computing. And moreover, the biggest advantage for the quantum theory is that in the traditional graph learning, we may take a lot of efforts to formulate the long distance information, and we cannot even balance better for the long distance information and the really close relationship. But for quantum theory, they have a quantum teleportation. So the current message passing based on GNNs cannot integrate long distance information. And with the quantum theory, the quantum coherence or entanglement will transfer the long distance information with a much faster time. So also, I suppose this is not the biggest advantage for just the quantum graph learning, is also for all the physics-informed graph learning methods. That is the transparency and interpretability. The black box graph learning is always a shortage for all kind of graph learning methods, but the quantum mechanics as well as other physics-informed graph learning techniques, especially for the quantum mechanics, it has a very comprehensive theory, together with the theoretical basis in the real-world experimental verification. So it can explain the existence of our physical world as well as all kind of data and all kind of phenomenon and economy. And with the help of quantum theory, the explainable or interpretable problem will be resolved also with the quantum graph learning. So I think this would be a very promising research direction, but I am also a beginner here. And I just finished one of the survey paper together with Professor Xia and Professor Hancock. If you are interested in it, I would be a warm welcomer for all of us to have a discussion on it. So the next comes to the real world application part. So it has really a lot of application for the deep graph learning. So I would pick some of them, some typical them to introduce. First is come with the group anomaly detection. So for the group anomaly detection, it is a little bit different from the traditional anomaly detection or traditional outlier detection, because we generally focus on one node, that is one outlier or several outliers, but we may generally ignore the pattern among the several outliers, or maybe one node cannot be recognized as an outlier by traditional method, but it actually plays a role in a group, but the group is an anomaly. So here we come up with several methods for different application scenarios. So first is information retrieval. The figure here is a figure that's from Professor Jie Tang's paper, and I think this is very clear to introduce, so I borrow it here. And they work on outlier subnetwork. The problem of outlier subnetwork, but this also exists in information retrieval, so I use it here. So if we use the information about the flights to Sochi, and we can get 3 subnetworks that connected to the flights to Sochi. But actually, when we want to search some information, I mean, we want to focus on the city, right? But these 3 subnetwork, they may get another flight and go away right now. So in the information retrieval results, this one is outlier. It fits and it maintains for the searching conditions, but it is not what we want. So such kind of outlier patterns always exist in our information retrieval. So we come up with a method that's using the user's purity conditions of candidate set, reference set, and for comparison set. And together with the heterogeneous network and with the metapath and with some other metrics, we can come up with another outlier patterns detection. So this would be one way to implement the graph learning methods to real world application. So another one is a fig reviewer group detection, and I bet many of you are interested in it, because the fig reviewer group detection is very easy to understand, and in real world we are full of such kind of spam. And because many stores or restaurants always employ a really large number of people to create the fake reviews in the online review systems to mislead or to attract new customers. So generally, such kind of fake review are produced by a group that they may appear in one short time, and they may be always some similar users. And so a difficult way is that we cannot have a directly way to detect these fake review group by our traditional graph learning techniques. So because we cannot capture the underlying relationships, so to better detect such kind of group, we need to combine the data, the method together to first analyze some data to dig out the features of such fake reviewers. And together with the metrics and the graph learning techniques, we first cluster the reviewer into several groups, and then using the evaluation metrics to verify that which group is the fake reviewer group. So this work is also published in the ICDM workshop, the first graph learning workshop also. And next, I would like to introduce some of our work that's using graph learning techniques on the epidemic prevention and control. So firstly, we come up with the city risk index. Also, this is comes from the data mining. We find that the CRI is related, the city risk is related to many reasons, to many factors, but we conclude them into 4 factors: the economic and technology, population and geography position. And then we come up with the CRI index to evaluate the city's infection risk. And based on this risk, we can use graph learning techniques to forecast a city's infection risk level, to give the guidance and suggestions for the residents and the policymakers. And also, we also employ the human mobility and the human behavior in using the spatial-temporal network, which just the professor also said, and to do the epidemic prediction. And this is also based on a graph learning technique. And within it, we also use the real-world data to verify the effectiveness of this proposed method. And finally, we also do some data analysis work during the COVID-19 by using the social media posts on Twitter and the Weibo. Actually, I should put this slide in the data part, but since the topic is quite close, so I put it here. And it is more about the data analytics, and by analyzing the underlying reasons with the social media posts together with the public policies, we can get some differences across the different countries. So this is also a very interesting work. So I suppose that's all what I want to share with you. So thank you. Do you have any question for me?
Thank you, Shuo.
Thank you. Can you see me now?
Yes, we can see you.
Okay, thank you.
Great. Do we have any questions? All right. Well, I'll start with one. Shuo, again, thank you for your talk. So you kind of had a segment on the motif-based learning and higher order graph structures. So I think this is a pretty interesting direction, and in the last few years, there have been, I think, a lot of really high quality papers in this direction. So one thing I'm curious about is these methods usually are not super scalable, from my understanding, because they require some combinatorial number of groups, either motifs or substructures or other configurations of small patterns in graphs. And so I'm curious if you've kind of applied any of these methods to larger graph data sets, and if you've found some good ways to like scale up the scalability challenges.
Okay, thank you. This is a very valuable question, and this is really good. Thank you. Actually, this is the most complicated part of the motif-based or the higher order based graph learning part, because when we implementing some maybe subgraph finding techniques, it is really time consuming, and for the corresponding relationship between the subgraphs or the some motifs or some small structures together with the real world pattern, it will limit the application for a certain scenario because it cannot be generally applied to each scene. And so I think that are really some shortage for the current graph learning, especially based on higher order structures. That is also the limitations, I think. And I think that would be also the limitation of the graph structure, because in the graph structure, we only have binary relations. We do not have higher, so-called higher order structures that are predefined by us to better enhance the graph learning. So I wonder if I answer your question. Thank you.